Hey everyone, welcome back to my YouTube channel. So in the last video, we had covered some of the groundbreaking works in the field of click chemistry, some of the historical advancements in click reactions, some of the great pioneers who contributed in this field, and certain applications of click reactions in different disciplines. Today in this video, we'll venture on to light the path in slow chemical transformations, whereby we'll come across what is slow photochemistry all about, importance of slow, fundamentals of slow photochemistry, and some of the techniques that are used in this particular domain to measure photolysis rate coefficients of photochemical reactions that occur within slow. So without wasting much time, let's get going.
Light the path in slow chemical transformations. Chemical reactions mediated by light are referred as photochemical reactions, the consequence of which is the creation of transient excited states whose chemical and physical properties differ greatly from the original molecules. So what is slow photochemistry all about? It is about understanding emissions from snow and their influence on atmospheric chemistry. As per Merriam-Webster dictionary, snow is defined to be a precipitation in the form of small white ice crystals that are formed directly from the water vapor of the air at a temperature of less than 32 degrees Fahrenheit or 0 degrees Celsius. In general, snow, ice, or ice cores, they are believed to be a high-octane archives detailing the Earth's atmospheric chemical composition and climate change over time. They hold the capability to delineate other aspects of atmospheric chemistry. For example, changes in chemical composition in certain atmospheric species like oxides of nitrogen. So what is the importance of snow? Snow helps in reducing surface heating by the sun. It acts as a good hydraulic resource for surface environments, a sink for contaminants, a transport channel for these contaminants towards the aquatic or marine ecosystems, but above all, to photochemically generate reactive trace gases and release them into the overlying atmosphere. Snowflakes are mere water crystals that can never be replica of another. Sunlit snow and ice. These two play an important role in processing atmospheric species. Snow is regarded as a complex, multi-phase environmental medium where contaminants can accumulate or undergo chemical or microbial reactions. As snow falls, it scavenges atmospheric contaminants and deposits them to the ground. The loss of these contaminants is due to the photochemical reactions within snow, which is later channeled towards aquatic and marine ecosystems. Whether the contaminants poses a threat to the ecosystem would depend on the chemical composition of the impurity that was driven by the snow into these ecosystems. Let us now see fundamentals of snow photochemistry. Organic compounds in the atmosphere that exist in particulate matter, like in solids, in liquids, and in gases, that originates primarily from natural followed by anthropogenic sources. Certain organic materials can be reactive, but there are other organic compounds like methane and halogenated organic compounds which are considered negligible contributors to snow reactivity. Why? Because of their chemical inertness. As per reports, there are several natural and anthropogenic organic compounds measured in snow, including alkanes, phenols, low molecular weight organic acids, and so on. One of the beauty of organic compounds is that it can directly absorb photons, thus changing the radiation balance within snowpack. They possess the tendency to create radicals that can react with other compounds in snow. Snow crystals or snow grains, they act as a sink for various contaminants or impurities. It is these impurities that may ultimately undergo reactive processes and generate trace gas products. Most of the mass of precipitating snow crystals formed by condensation of water vapor onto an ice-forming nuclei, or by the freezing of supercooled droplets onto growing ice crystals, a process which is called as Rimming process. Rim snow is usually more concentrated in impurities than snow formed solely from the condensation of water vapor. So these ice-forming nuclei are a source of impurities in snow crystals. And so are the cloud condensation nuclei that nucleus supercool water droplets. Materials that can probably act as IFN or CCN are plant debris, bacteria, minerals, and so on. What happens once snow is deposited on the ground? After the deposition of snow on the ground, snow crystals in the dry snowpack get subjected to temperature gradients. This generates water vapor fluxes between crystals. These fluxes causes the sublimation of one part of the crystal and condensation on the other part, resulting in a change in snow crystal morphology. This sublimation condensation cycle that occurs also leads to change in physical properties of snow, like density, hardness, specific surface area, and so on. The processes that lead to snowpack metamorphism occurs on individual grains, but results in bulk compositional changes to both physical and chemical properties of snowpack. Several processes can lead to such changes, like freezing of supercooled droplets during fog events, photoreaction of snow species between themselves or with atmospheric gases, and processes that are linked to snow metamorphism, like release of adsorbed and dissolved species. Sublimation and condensation cycles during metamorphism have potential to release or trap dissolved species. Additionally, they have the potential to change snow and atmospheric composition and make these species available for gas phase or surface reactions. So what affects the impurity concentration in snow? Any type of physical or photochemical processes, action of freezing, even the natural freeze-thaw cycles that occur in snow and ice can contribute to a decrease in impurity concentration in snow. Let us now see the important electromagnetic spectral regions where photochemistry within and above snow is most likely to occur. UV spectral region is the most critical for photochemistry in the atmosphere and in snowpack, because photons of this region possess high enough energy to break chemical bonds and low enough energy to penetrate the ozone layer and reach the troposphere. Our sun splits the UV radiations into three spectral regions: UVA, UVB, and UVC. The energy required for radiations of UVA spectral region to pass through the ozone layer is sufficiently low, with little attenuation, due to higher wavelengths. This region is therefore reflected back into space the most by our planet's surface. This region is therefore very slightly dependent on overhead ozone and solar zenith angles. Species like nitrogen dioxide, formaldehyde, nitrous acid, bromine oxide are all reported to be good UVA absorbers. UVB region, on the other hand, they possess a slightly higher energy than UVA region, just enough for it to partially penetrate through the ozone layer. Because of this, the UVB region gets capable of photolyzing tropospheric ozone and producing certain radicals like hydroxyl radicals. UVB regions in the troposphere are therefore highly dependent on tropospheric ozone abundance and the solar zenith angles, which determines the path of light through the stratosphere. Species like ozone, bromoform, and nitrate ions in aqueous solution are reported to be good UVB absorbers. Finally, UVC region is a spectral region where the radiations are completely absorbed by ozone and normal oxygen due to shorter wavelength. In other words, these radiations are blocked and is not allowed to reach our planet's surface. Why? Because this region can generate ozone in the stratosphere by splitting the molecular oxygen into corresponding oxygen atoms, which later recombines with other oxygen atoms to form ozone. Because of this, the UVC region is not of much relevance to tropospheric chemistry. Solar zenith angle, ground reflectivity, and the overhead ozone. These are reported to be critical parameters for considering photochemical rays. Albedo effect is nothing but how well our planet reflects sunlight. And this can vary as you go from one region on our planet's surface to another. High albedo surfaces like ice are great reflectors, sending most sunlight back into space, while low albedo surfaces like oceans absorb more solar energy. UVA region, being reflected the most, is regarded to be one that shows a significant albedo effect. So does the UVB region. But due to their long light paths, the intensities of this region is greatly attenuated, causing the photolysis rate of UVB absorbers to be up to an order of magnitude smaller in high latitudes than at mid latitudes. Photolysis rate coefficients within snow are measured using chemical actinometer. So how do photons penetrate in snowpack? When radiation enters the snowpack from overhead, the scattering of those radiations alter their path, converting them directly into diffuse radiation. This scattering ultimately redirects the light back upwards and out of the snow, leading to a high albedo of snow in visible and UV regions. The scattering also enhances the path length of photons in snowpack, thus enhancing the absorption probability and photochemical rates for trace absorbers in snow. Both scattering and absorption combine non-linearly to control the depth to which photons on an average penetrate the snowpack. For diffuse radiation and deep and uniform snowpack, the attenuation of light follows Vogel-Lambert's law, which states that attenuation of light varies exponentially with depth, and it is given by the equation 1, wherein ID is irradiance at certain depth d, and alpha naught lambda is nothing but asymptotic flux extension coefficient. This E-folding depth, which is the depth over which the intensity of radiation decreases by a factor of E, is related inversely with asymptotic flux extension coefficient. It thus became quite evident that the penetration of light into a snowpack and thus the amount of photochemistry within snowpack is highly dependent on solar zenith angle. This effect is caused by the fact that snow grains typically act to forward scatter the light that interacts with them. Thus, for glancing incidence radiation that is characteristic of high solar zenith angles, a greater fraction of light is scattered back to space. This enhances the albedo, and less light enters the snow to drive snowpack photochemistry. A chemical actinometer, as mentioned earlier, is a technique that is dedicated solely to evaluating the photolysis rate coefficients within snow. A normal actinometer works on certain distinctive modes of operation, namely static batch mode and flowing gas mode. In static batch mode, the measurements with respect to changes in gas composition are taken on certain fixed time intervals in which the photolysis reactor is exposed to sunlight. This photolysis reactor is filled with an actinometer gas and is kept unexposed to sunlight by sealing off the reactor by a gas valve and covering it with an opaque hood. In the flowing gas mode, the analysis of composition is performed using an online gas detector that detects the gas passed through the detector. In this case, a time interval is considered to be mean residence time of the gas in the illuminated reactor, and the actinometer gas is constantly passed into the reactor that is exposed to solar radiation. Applications of this device is in meteorology to measure solar radiations emitted by sun, in photochemical experiments, and it is also regarded to be a first choice for calibrating photochemical detectors used for radiation measurements. Depth-resolved photochemistry is regarded to be a technique evident for its depth analysis within snowpack. It determines the photolysis rate of a particular photochemical reaction by measuring molecular fluxes within snowpack and by performing certain calculations made by developing different model systems that would possess the ability to predict the photolysis rate coefficients at any number of depths within snowpack. Different models as reported in the literature can be used in calculating photolysis rate coefficients of the radicals produced by photochemical reactions within snowpack under study. Of course, with appropriate assumptions. To name a few, we have the SORT model, that is discrete ordinate radiated transfer cone model, TUV snow model, tropospheric ultraviolet and visible radiation model, packed 1D model, 1D atmospheric chemistry and transport model, and so on. The SORT model calculates the photolysis rate coefficients with appropriate assumptions of species undergoing photolysis within snowpack. Likewise, TUV snow model, this allows optical characterization of a snowpack from the knowledge of albedo and light transmission into snowpack, without the need of the knowledge of snow grain size. This model can predict photolysis rate coefficients at any number of depths within snowpack with a minimum resolution of 1 mm as reported in the literature, provided that certain conditions like absorption and scattering coefficients, snowpack density, time and location, ozone column depth, and sky conditions are known to us. PAT 1D model, again has been influential in understanding certain halogen emissions from snow on boundary layer oxidation processes, In other words, to understand the combined impact of snow emissions and boundary layer dynamics on atmospheric chemistry. So here, several such numerical models are developed or perhaps in a developing stage that can prove to be most useful tool in snow photochemistry and its influence on atmospheric chemistry across the globe. Thank you.
Thank you very much everyone for joining me to light the path in slow chemical transformations. I can't wait to invite you again in my next video. Do like, share and subscribe to my channel. See you in the next video.